Hello, everyone. My name is Joe Barco, and I'm Senior Director of Workflow Marketing at Unchained Labs. I'll be your moderator, and thank you for joining us today. I apologize for cutting the pong game short, but spoiler alert, Junior is always going to win. Today's presentation will focus on software and data integration. When most of us think about lab automation, we think about liquid handling, powder handling, maybe some of the reaction setup. This could be a fully automated system like the Big Kahuna, or smaller distributed operations on a series of juniors. Increasing throughput for experimental setup increases the need for data throughput as well. Some of these may be able to be physically integrated into the lab automation setup. Some of that might not be possible because the instrument is too large or the read time is too long. LEA, our laboratory execution and analysis software, gives you an approach to integrate all your data in one place, whether they share a physical space or not. LEA as a software package includes experiment design through Library Studio and Design Creator, experiment execution through Automation Studio, and optionally analysis through Polyview and LEA analysis. Data can also be visualized by many other approaches. Georg will soon speak about the way they enabled a larger group of chemists to design experiments to run on their junior, but allow me to give a brief intro to Library Studio and Design Creator first. Library Studio provides a number of intuitive ways to set up your plates and design your experiments in a way that makes sense and that enables the powerful data analysis processes. You can enter specific chemical information to be available in the chemical inventory, and even use equations and ratios to design your experiments. The software has a visual layout that allows you to design your experiment directly in your reaction format. Design Creator walks you through the rest of the experiment process by showing you all the capabilities your automation system has. You can drag and drop steps in the order in which you would like the experiment to be executed. It guides you along the way by highlighting fields that require information and won't allow you to move forward before filling them in. When finished creating your design, Design Creator has validation capabilities that will tell you if there are issues with your design and give you specific instructions on what to fix. You can then go back to that step, make the necessary changes, and then finalize your design. Several of our customers and collaborators are presenting on their lab automation systems with us this month. Today, we'll hear from Georg. Next Tuesday, May 25th, Paul Clark will talk about Dow's approach to automation and how that has impacted their product development. Last week, we heard from Professor Doyle at BMS, Professor Doyle from Princeton and Jason Stevens from BMS, and how they coupled new machine learning strategies with their lab automation. Go to our website, www.unchainedlabs.com, to review past event recordings and to register for future presentations. We'll have a Q&A session at the end of today's presentation. To ask questions, all you have to do is click on the Q&A in the Zoom navigation bar that's at the top or the bottom of your screen and type your question. We'll get to as many of them as we can, and if we don't get to you, we'll connect you with our speaker after for follow-up. Now, I'd happy to introduce our speaker today, who's Georg Wuitschik, a principal scientist at Roche. Georg has strong backgrounds in synthetic chemistry, completed his master's degree at Stanford, working with the Trost Lab, his PhD at ETH Zurich, in the Carrera Lab, and did a postdoc at Cambridge University in the Ley Group. He's been with Roche since 2011, working in process research and development from that time until 2019, and has been building a high-throughput experimentation lab since then. Georg's talk today is entitled Making High-Throughput Experimentation More Accessible and Efficient. Thank you, Georg, for joining us. The floor is yours.
Hello. Yeah, thank you very much. Thank you, Joe, for the introduction, and thank you very much for giving me the opportunity to present today. So today's talk should be about how we as Roche approach high throughput screening, in that we'd like to have a model that serves all the way the value chain from medicinal chemistry to late process development. And I'm just standing here for a team of 3, but which you see here on the screen. But also, there are a lot of people supporting us. We wouldn't be here without the analytics, without the engineering, building the stuff, building the labs. And so, this is just a small glimpse of what it takes to have a lab running like that. And with that, I would like to jump into the introduction. And here, for all of you non-chemists out there, this is what life as a chemist looks like. You start with an idea, and you then design a few experiments. You test your hypothesis and you analyze, and then it goes down the circle again. And your experiments, they typically look something like this, where you have 2 or 3 ongoing at the same time, and that's what your life looks like. My job, when I got that one, was to say, okay, how can we do that better for certain cases, or for these many cases where there's just too much stuff to try. For example, consider this Buchwald Hartwig reaction, where you have all these parameters and possibly a couple of other more that you could change. And typically in these cases, you don't really know what could be good reaction conditions. There's usually a huge difference between very similar reaction conditions. So changing a base, for example, will completely kill the reaction or enable it. And so when you start working on a reaction like this, there are many, many things to try at the beginning. And so when there are many, many things to try, you want to be able to try many, many things at the same time efficiently. And so this is typically how it looks like here. We have plates of 24, or in this case 96, which we run, and then we analyze them in these sample plates in our LCMS. So how does that look like for us? How does the actual workflow look like, and why am I giving a talk today about it? So in terms of workflow, we have a quantos solid dosing system. It fills the plates with one of these 32 solids that are up here. And then afterwards, we have liquid dosing, which we either do using our junior or using pipettes. And then the reaction execution is done on the junior, where it's heated, cooled, steered, whatever you need. And afterwards, a sample is taken and it's measured on our LCMS. So you could think, okay, that's the workflow done. But in order to get to that practical part of the workflow, a lot needs to be happening beforehand. And so that's what I want to talk about now. So here's the execution. It's exactly what you saw here. And underpinning that execution is the plate design. You need to know what you want to test and how you want to test it. So what kind of reaction temperatures, what kind of components you want to have in there. And also you need to know what you want to measure, like what are your analytics, what kind of side products are you expecting? Do you have reference standards that you want to integrate so you get absolute yields at the end? All this is stuff that you really would want to know beforehand, before you can go into the execution. And then afterwards, after the execution, you get a lot of data. You have all the input information, how much has been weighed into the plate at each position of each compound, what kind of structures are in there. And then, of course, all the information that comes from the analytical side down here. But, analysis is nice, but you have a customer, he or she needs to know what works and what doesn't. So you need to visualize it, and you need to visualize it not only in the context of the plate that you're working in right now, but also ideally as a lab, you want to be able to learn across projects. So you would want to answer questions like, which catalyst gives how much hydrodeboronation on which kind of substrate class? And if you silo all your data in one in each individual PowerPoint files or Excel tables, you will have a really hard time answering questions like that. And you will basically waste a lot of the potential of the data that you have. So how do you integrate all that? I mean, as you know, we have a junior, we have a quantos. Somehow, you would want to be able to design a plate. You want to do all that stuff without copy pasting endlessly between different programs. And so this is how we do it. We have a Google Sheet. It has not much to do with a normal Google Sheet. You will see it in a minute, where you can do all the plate design, where you can register reactions, you can register reagents, you can do data corrections. It stores all the data in data tables. So it's really the underlying fundament. And then you have the execution. We have the Library Studio, we have Kronos, and then we have input files for LCMS. All that stuff needs to be generated by the Google Sheet. Also, you want to have labels. You want to have emails telling you when a plate is finished. You want to have lots of other stuff surrounding it. Trello integration, and like stuff that really makes the work easier and reduces errors. So here, data analysis, the actual amounts, what kind of retention times, peak areas, mass peaks, what you have actually in there, that we do with ACD, Spectros. And then in the data analysis part, all that data is sucked into Spotfire, where we calculate yields and do cross-project comparisons and all that good stuff. So that's how it works in theory. And in a second, I'll show you how the workflow looks like in the actual Google Sheet, which you will also be able to download for yourself to play around. But before that, let me give you a shameless plug of a paper that we published last year, in which we looked at all the 60 whatever thousand publicly available Buchwald-Hartwig reactions that you find in SciFinder, Reaxys, and other public databases, and then out of which we extracted what are good or typical conditions for whatever substrate pairing that you may want to work with. And this is something that we are using now on a day-to-day basis whenever we have a Buchwald-Hartwig reaction, because there's so much you can learn from that stuff, or at least we think we can learn, that is not found in review articles or in databases, that we find that super useful, and maybe you want to have a look at it. And with that, I will skip over to the demonstration, in which I'll share my screen. So here you have our Google Sheet, and the Google Sheet has different parts. And the initial part is the one you see here, where you can register reactions. Of course, this is not how you would normally do it. Normally, you would connect your Google Sheet directly, or whatever sheet directly to your ELN. But since different people have different ELNs, this is what we put in here. And you can see here that you have starting materials, you have product, you have side products, and you have some categorization that you can later do analysis with. And here you can enter your reaction information, and it has some, let's say, half intelligent features to it. So for example, you can have a look at everything that the database knows already, and you can use that. But more importantly, you can, for example, also enter new information into the sheet. So for example, here 2-nitrotoluene. Then the Google Sheet goes into Google, retrieves the cast number, and then tries also to find smiles, inchy keys, and densities, and whatever you want. Sometimes that works, sometimes that doesn't work, but you can see here, here you can then directly jump into the information, for example, on Sigma Aldrich, and copy paste it if you want. It also, because it's Google, recognizes a lot of abbreviations, for example, B2Pin2, or whatever other crazy chiral resolution reagents you may have. And now it finds the cast number and finds all that information. So now assume that you have your reaction registered, either through the ELN or through Google Sheets. How do you build a plate? How do you know what you want to do? So here you can see the plate builder module. I have to reload now because from time to time Google has a habit of forgetting stuff, in this case the buttons to press. But what you can do on that sheet is you can say, okay, I want to have 12 catalysts, for example. I want to have solvents. I want to have bases. I want to have all that stuff. And but in this case, maybe I want to just start from an empty plate. So I empty the plate and say, okay, give me palladium catalysts, give me 12 of them. Maybe I don't want to have the triphenylphosphine palladium chloride in there. Maybe I want to have one of these. All these are included, of course, so with all the data in the sheet. And it also tells you, for example, which ones are on the quantos right now. So which ones are ready for dosing without swapping the heads. So say I want to have this. Then I want to have, well, maybe that one here and that one. Then I want to have solvent. I want to have a choice of all solvents, maybe 3 solvents. For a Buchwald Hartwig, ethyl acetate is not that great. So yes, let's use T-amyl alcohol. And then here we want to have bases. Let's have, for example, a few strong bases, maybe also KH and DS, because DS, because you also want to have something strong in there. Okay, now you have your plate. Over here, you can decide which of the permutations that are possible here you want to include. So here you have now 9 permutations. Maybe I don't want to have KH, MDS, and T-amyl alcohol. Doesn't make much sense. Okay, now I have a plate. And with that plate selected, which you can, by the way, also always save under new name, so you have lots of template plates which you can then save and just retrieve to whatever extent you want. We go into file generator. So the plate is loaded here already. Up here, you select a reaction. So 2 reactions are included, but I'll just stick with that one and say, okay, I want to convert, say, 3 milligrams. I want to have 1.3 equivalents of that. Of course, you can change which is the limiting reagent. I also want to include an internal standard, which should go into all of the different vials. So say 0.3. Of course, this could be anything else. So if you have a constant reagent, it can go there. Then down here, you have all the components that are on this plate. So it's all those over here. And you see here, you can choose, for example, that I want to have maybe 0.05, so 5 mole % of catalyst, or if I'm doing something for medicinal chemistry, typically the numbers go up, and I go to 15 mole %. See, the numbers change accordingly here. If you say, oh, I want to have more of that catalyst, of course, that's no problem as well. Base amount, that's fine, typically. Maybe, oh, K3PO4, or know that I have an aqueous solution here. So I switch that over, and then it knows all the solutions that we have on stock. So it tells you how much volume you need of each. And with that, that's how you generate the plate. So down here, you fill in reaction time. So in typical, you have 180 minutes, 80 degrees. You can also set stuff like liquid overage for your junior afterwards. You define a plate purpose, something here, and then it says, okay, ready to submit. And you can click the button. And afterwards, now what it does is basically it generates the dosing file for quantos. So it knows, which catalyst goes where, how much. It generates the LCMS input file. So it will look automatically for all the starting materials, products, and side products, and the LCMS then tags that. And it also generates sequence files for Agilent. It generates a cheat sheet. It generates lots and lots of data. So, all these different files that you can see here. But what I want to show you, because now we're in a junior seminar, is how the junior file looks like. So let me just drag that over. So I opened a file, and here you can see what happens then in junior. So the junior is super like the library studio. So library studio is super powerful, can do a lot of stuff. But since we know we only want to do a certain kind of stuff in a certain repeat fashion, I can like guide library studio more than it would be possible with a template farm. So if you look here, so you have a reaction plate, it's automatically generated. You have a sampling plate, you have source plates, which are automatically generated. And then you also have all the transfer steps generated. So if you go through that reaction sequence, it starts filling up the source plates, stuff which you normally will do by hand, and then fill up the stuff. Now you start transferring stuff over to the reaction plate, go down, 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 down. So, and then down here, it sets the steering rate, sets the reaction timer, sets the delay, sets the heating temperature, cools down, and then takes a sample and fills everything in there. And that's the end of that story. So you can see there are advantages to that, but there's also a certain amount of freedom that you have to sacrifice. And with that, I jump back into the presentation because there's one more slide, basically the disclaimer kind of slide. So why would you want to build your own junior input files, and how do you do that? For me, the biggest motivation was to save time and avoid errors. I really did not want to juggle template files, which I have to modify on each machine for each different purpose. I want to have everything enclosed in one big shell so that I don't have the problem of having inconsistent data. I want to have something that is super easy to use, even for somebody who's a casual user. So this could be people like visiting and wanting to run their own stuff. This could be technicians. This could be interns, which you want to get productive very quickly, like lots of motivations. And for that, in order to generate your own junior or library studio input files, I analyzed the file structure, and it was quite pleasing to find that it's a simple XML file, and it's really not that difficult to reverse engineer. So this is how you do it. And you can also generate your own XML files using the gSheet and modify the stuff. Joe will later share that link to that public version of that Google Sheet, so you can have a look yourself. There's one thing that is still a limitation, but that may change in the future. You still have to go through Design Creator before Automation Studio will run your file, because the database that is behind the junior doesn't know about all these processing steps, so you have to kind of teach it. Okay, and with that, I would say thank you very much for your attention. This is me standing in front of Quantos. This is my lovely assistant, or the technician Vera, standing in front of our junior. And yeah, so bring on the questions.
Thanks, Georg, for your presentation. One thing before I get to the questions, so what I see is a couple of things. One is that it allows your chemists to be chemists, right? Where they can design their experiment as they would want to set it up without having to learn, this is how I set up a plate map on Quantos, this is how I use Library Studios. They can design it, and all of that stuff is done in the background, right? So they can focus on being chemists. Has that been the experience so far?
Yeah, so far the uptake was quite positive, I would say. Like, of course, it's Google Sheets, so there are glitches from time to time, but it also allows you, to be much more flexible in terms of what you want to handle. Yeah.
And is work primarily done on the junior through the gSheet method? Like how has it kind of been kind of uptake or throughput been using this method?
I can say that I think we ran some 9,000 experiments or so in the last year, like individual vials. I would say pretty much whatever we do on Junior, we run through the gSheet. Because, like even stuff that it can be easily done in Library Studio, if you're familiar with the gSheet, then you just quickly do it through the gSheet. Yeah.
But I think also from that point of it's all in one centralized location too, right? So then other people can see what's been run on it.
Yeah, and it has Google Drive, right? So it synchronizes between all the computers automatically. I don't have to take care of anything of that. So sometimes it's good to be in a walled garden, because it's nice and cozy in there. So.
Okay, thanks. So we have a lot of questions that have come in. So if you have questions that you still want to ask, as a reminder, if you go to the Q&A section at the Zoom navigation bar, you can type your question and we'll get to as many of them as we can. So your first question is, why did you opt building your own system instead of using a commercial solution?
Yeah, I mean, if there had been a commercial solution that integrates Quantos and Lea at the point when I was faced with having one, I think we wouldn't have built one. But since there wasn't one, there there was only this one option. Now I think there are possibilities, but like we're quite happy with the deep integration that we have. Like all the email functionality and all the stuff that I couldn't share today. Yeah. So.
And another question is, can your tool do everything that Leah does? And I think you kind of said no on this, but what are the constraints at the moment with the tool in comparison to Leah, Library Studio?
So, like in Library Studio, you're much more flexible in terms of what you can do. So, for example, what my tool does is, there's always one set of conditions in one row, one set of conditions in one column. Of course, there's no such limitation in Library Studio. You could have 24 different catalysts in a 24 plate. So there's also, I'm exclusively using the 6-tip because we find that this is just so super fast in terms of transferring stuff, and so we don't use the single tip. And so, with that comes some limitations in that, the number of columns always needs to be a multiple of 6. So it needs to be a 24 plate, or it needs to be a 96 plate, where you have, you are able to use that 6-tip. So,
okay.
And I'm sure there are many, many more limitations that we haven't thought about because, we built this for our use case, but maybe, it's useful for other use cases as well as people play around with it and modify it.
So there's certainly a number of questions coming in about that type of thing. So probably this is closest to that, which is a question about, do you normally run the same type of chemistry, or do you switch between catalysts like palladium to magnesium?
Yeah, we switch all the time. We have, I think, like 300 or 400 different compounds registered on the system. So we do Ullmann couplings, we do palladium, we do amide coupling, solubility, chiral resolution screening, whatever, yeah.
Okay. And then can you elaborate on your data visualization tool that you use for the high throughput data, and how do you present into users internally? Like, what's the best way?
So I'm still building that. You saw these screenshots. So basically, it tells you what kind of yield, be it relative or absolute, you have in your reaction mixture. It shows you all the spectra in overlay. It's just a simple Spotfire visualization. It's not that difficult. We also have a tool where you basically goes through all the PDFs of all of the samples and takes screenshots and puts that in a matrix. But yeah, it's really like that's still ongoing work, so to say. But yeah, once you have all the data in place, that's not so difficult. So
I think a few other questions. How many people are in your high throughput screening team? Like who actually kind of run it? Is it just
so
3
right
people?
now we have, it's the 3 of us. Yeah, but we are kind of drowning in requests. Because once people get the taste of it, especially medicinal chemistry, and they go away from single-digit yields, they want more. So yeah, we look at expanding that whole operation at some point.
And then maybe more technical question, which is the reformatting the plates before analysis done in Junior or done separately?
Like the reformatting of the plate. Oh, you mean the how many equivalents of what catalyst or so? No, that's all done in the gSheet. You once you click that save plate button, it generates the data. If you want to change stuff afterwards, you just generate a new version of that plate, just save again, and then it generates a new file. So everything is done in gSheet. You can, of course, change that later as well, but that's not the plan. Yeah.
Okay. And then a question, I think maybe more on how did this kind of come about? So is there a template for high throughput screening design in gSheet, or did you just basically create this from scratch? gSheet's just
no,
right?
no. gSheet doesn't know anything about chemistry.
Yeah.
It doesn't know how to draw structures, anything. But you can teach gSheet a surprising amount of stuff. So yeah, no, there's nothing.
You just did it all.
Yeah.
Okay. And then can the Google Sheet be applied to other automated synthesis platforms, like
in theory it can, but so let's say it's not difficult to because once you have all the data in the Google Sheet, it's available in a data frame, and now you can generate whatever CSV, XML, JSON, or whatever file you want. So that's not difficult, but we haven't. So we only built what we needed.
Right. And I have two more questions at the moment. So one is, if my organization doesn't use Google Sheets, can you still use the tool?
I guess your organization wouldn't want to use it on your private Google account. So with that in mind, I think you're kind of stuck, although the source code is fully public, and Excel, I guess that's what you would be using, also now understands JavaScript. So, I wouldn't vouch for it, but I think there's a decent possibility that you could get it to run quite easily. Like, not easily, but you could get it to run. You
And
wouldn't have to translate to VBA. Yeah.
Okay. And I said one more question. So this is the last one, which is, since the setup was made on being versatile and user-friendly, do you see challenges in terms of how you implement data collection to be more future-proof? And then the question, the person asked about specifically about implementing across different lab tools, or like a machine learning AI approach. Have you guys kind of thought about how to move it that way?
Yeah. So, I mean, you saw that advertisement for the paper. And of course, when you analyze all the data that is out there in the public domain, the next thing is you want to analyze also all your internal data and make predictions about what should be the right plate. And so, yeah, we are actively working on that. And all the data that we are generating is intended to go to machine learning, but it's not going there right now because, it's one of the many things on our long to-do list. So, yeah.
Okay. One more, sorry.
Yeah, no problem. Yeah.
Can you describe so the bug you showed about Hartwig's set of data. So how do you use that data at the moment? Is there a way that you use that data to generate the next plate of reactions? Is that automated, or is that chemists looking at the data and designing the next set of experiments?
Right now, it's me looking at the data, but I followed last week's talk, with a lot of interest. And the Bayesian, learning, for example, would be a great way of applying this, because you could easily tie that into feeding the results and then getting back a new suggestion. Yeah. So right now it's me looking at it, but things will change. Yeah.
Okay. Thank you again for your talk. It was fantastic, and thanks for walking us through. For our attendees, there's a link to download the gSheet that Georg generously shared with us, which is in the chat, and we'll send that out to you afterwards as well when we send the recording. So thank you, Georg, again. Thank you, everyone who joined us live today. And if you want to have a more deeper conversation with our speakers, or we didn't get to your question today, please get in touch with us at info@unchainedlabs.com. And we'd love to connect with you. And if you love the seminar and want to learn more, please go to our website and check out our upcoming events. Thank you, everyone, and have a great rest of your day.